So good day, everyone. This is Maciej Hruszowski of Red Hat Research, and I would like to welcome you to another Research Days event. Please let me introduce our main speaker, Professor Paolo Missier of Newcastle University, joined by Red Hat's Senior Principal Software Engineer, Ivan Nečas. Gentlemen, welcome, and I will leave the topic introduction to you. The floor is yours.
Thank you. Thank you, Maciej. So I guess I'm taking over, right? Ivan doesn't have to say anything now. Thank you all for joining today. So I'd like to start by introducing myself very briefly. So I'm Paolo. I'm a computer scientist in the School of Computing at Newcastle University. My teaching, just to give you coordinates, is on big data analytics. My current passion is data science for health, so health data science. And really what I would like to talk to you about today is a story about data provenance, which is an old passion of mine, and is essentially a story about how metadata can make your life better is in two different settings. One is essentially software engineering, and one is in making data science pipelines more explainable. In fact, the original title that I've thought about for this talk is analytics of analytics pipelines. Okay, so basically, how do you do analytics on analytics pipelines? This is talk in two parts, and necessarily the first part especially will be like a slice through a piece of work that we did a few years ago, which is quite complex, and I'm not going to do justice to it, but I'm going to basically cut to the piece where provenance appears, because that's kind of the main story here. It's called ReComp, and it's about selective recomputation of analytics workflows, which are expensive and need to be repeated often. And the second part is data provenance for data science, which is a more recent piece of work that we've been doing with colleagues in Southampton and in Rome, Italy. Okay, so just to get started, the first part, really brief overview on ReComp, and the context is data science, as we know, has got this magic analytics box where big data comes in on one side. Trivializing, but for the sake of illustration, the other important part here is all the meta knowledge, basically libraries, tools, reference data sets, especially here. And what we're interested in is study what happens when each of these elements essentially evolves over time. Basically, it's about tracking changes and reacting to changes either in the inputs or in any of the meta knowledge, or especially the reference data sets we have that may change. Okay, and so here's a driving example just to fix ideas, which is also the example that you'll find in pretty much all the papers that we've published on this. In the area of genomics, some of you may be familiar with a complex pipeline, which is actually kind of compute intensive. So these are our own measurements on using Azure on Azure Spark cluster. One exome takes about 10 hours to process. An exome is like the standard kind of 2% of your genome, which is informative enough to give interesting insights into potential genetic diseases that you may be carrying. And in fact, the second part of this pipeline is the much smallest process that we're focusing on as a case study here. It's very lightweight, so it's really not, in terms of scalability, in terms of scale, very heavy in computing, but it has the characteristics that we want to do experiments with. And it basically takes the set of variants, there are about 30,000 variants in your exome that may potentially be compromising your health. And then you come in with a phenotype, which is disease hypothesis. I think I'm looking for evidence for this particular phenotype. It can be a genetic disease. And then this process here will make use of a couple of auxiliary databases in blue here, or maybe in ClinVar, as variant databases. and we provide a classification of the variants, limit down to maybe 100 of them or less, and say for each of them, this is no worry, this we don't know, and this is definitely a red flag for you, okay? And that goes to essentially clinicians for further testing and diagnosis. Okay, what do we do with this? Well, we look at what changes over time. And so we focus, for example, on CleanVar here. And this is a simple comparison of the state of knowledge, essentially, on variant and their meaning between 2012 and 2014. We first published this piece in 2015. And you can see that there's a substantial change. Okay, so you definitely want to track these changes, which means that you have to go and consider rerunning this process over and over again. CleanVar changes every month. And in fact, is what I call a game of battleship. It's a matrix that says, okay, on the rows, you have the monthly version of CleanVar in 15 and 16. And on the columns here, you have patients who have one of these diseases. And the black dots indicate that the diagnosis for this patient has changed because of a change in the version of CleanVar, or A15 in this case. And in this patient here, it has been affected by changes in CleanVar here, but not until 11:15 when maybe some of the variants that this person would carry that was on unknown significance became then known as, oh, this is a deleterious variant. Sorry about the bad news. And so basically, CleanVar tracks the evolving state of genetic knowledge, and then we want to carry it through to the cohort of patients that we have diagnosed in the past, keep them around, and re-diagnose them as things change. Okay. Now, this is a kind of a toy example in terms of scale, as I said, but it's still illustrative because you can see here that there's basically out of about 500 executions that potentially we need to redo, only about 14 really would be the ones that we really need to know about. The others are basically a waste of time. Okay. So how do we try to avoid this waste of time? So let's first kind of formalize a little bit, just very light touch. Yes.
So to interrupt, just there was one question towards the previous slide about the meaning of the different dots and empty boxes. There's also the red boxes. So
yeah, thank you. So by some miracle, I can actually see the chart today. So the dots is actually no change. Basically, the changes in the version, like in this case, do not affect these individuals here. The white squares say yes, these changes here. So basically, these updates to the database, this version of the database now affects, includes some variants that are carried by these individuals, but it doesn't change the destiny. Okay, we don't have any new bad news or new good news in some cases. In fact, to answer the question, the diamonds is actually very few good news, where something of uncertain significance or declared deleterious has later to be found benign, and therefore we can actually, in rare cases, we can re-diagnose and report good news in this case. I hope that answers the question. Okay, so as I was saying, basically, this is a very simple case of you computing a function from with input vector X to an output vector Y with additional dependencies D, and the Ds are these two databases as in this example here. It's straightforward. And it's just to say, well, how can you possibly react to changes? Just to clear the field from the obvious stuff, you can always refresh. Simply recompute, get a Y prime by recomputing F on X prime and D prime. That, as I illustrated a minute ago, is likely to be expensive and wasteful. Or you can approximate. So statisticians love the idea of inventing new functions that are surrogates for the real functions and that are cheaper to and less expensive to compute. This is very domain specific and takes a lot of effort to figure out these new functions. This is the emulation approach. The approach that we have suggested is like is the following. It's basically you try to estimate. So you have a notion of distance between 2 points in the input, or 2 points, 2 versions of a database. Okay, imagine a distance between 2 versions of the database, and correspondingly a distance between 2 outputs. Okay, and so this is the distance between the 2 outputs, and we want to try and estimate this distance without explicitly computing the new outputs. So you have the old output, we have the distance between the inputs or the versions database, and the challenge is to try and estimate the distance, not the new output, but the distance between the new output and the old one. Okay, and you say, well, if that is larger than the threshold, then I go ahead and recompute, because basically that distance gives me a notion of an impact of a change. So impact, a change in input or in the dependencies will impact the output to some extent. And now there's a good case where things are well behaved. This is like it's called a stable function, such that if the distance between the x and x prime, like here, is small in the input, then if a function is stable, then you can rely on the fact that the corresponding distance delta y will also be small. And therefore, because you have epsilon x, which is delta x, so well, if this is less than a given threshold, then I can guesstimate, okay, that the corresponding distance here will be also below a threshold, and I don't have to worry about it. And if that's not the case, then you recompute. So if this epsilon y is greater than delta y, then you recompute. Now, unfortunately, the problem arises. So you can solve this problem if you have a well-behaved function. The problem is when I have transformations are non-stable, and so in this diagram here you have a small distance delta x, but that basically translates in a big distance delta y, and furthermore, this distance really is type dependent and application dependent, and it may not be well behaved at all. So for example, in our example here, it's possible that one single variant that gets updated in one version database will now be a disaster for someone, and it can be entirely possible that an entire set of variants that are changed in the database have no effect at all. Okay, so this is an unstable function. So we set up, so there's some more detail here, which I'm not going to go into, but effectively, the problem, so we have 2 problems now, okay? So the first is one of scope, understanding which cases are affected, okay? And you can use heuristics in this case. For example, if you're lucky, you can inject a heuristic into your process and say, well, a change can only have an impact on a case if that change, the variant, is associated with the same phenotype as one of the patient. So you basically look at the phenotype that you're looking for the patient, the phenotype phenotypes that are associated with the variant. Basically it reduces to a query, and it's easy to compute.
Would this heuristic?
So if you do this,
may I ask?
Yeah. How can you know there's no impact on patient without processing the data? Yes. In general, you can't. So that's that is exactly the problem. The function is unstable to the extreme. What I'm just giving you here is a conservative rule that says, conservatives in the sense they will not produce any false negatives. So if you're potentially affected, you will be processed. Okay. So if I execute this query and I see that patient X as the same phenotype as one of the phenotypes that's associated with a variant, then I don't know if that will change the destiny of the patient, but I will reprocess that patient. Okay, so I conservatively reprocess all patients where potentially there will be some impact. But I can exclude the ones where I know there's not going to be any impact in this particular case because I have the semantic rule, if you wish. Okay, so
Regarding
it's basically, yeah, go on.
That semantic rule, like, is it always need to be manually put, or there's also a way that the system would kind of infer like the relations between the inputs and outputs?
So this is unfortunately not much that we can do about this. What I'm getting into is an architecture that essentially keeps around all the relevant information about every past execution, so that you can basically determine, you go over that history and determine who is in scope and who is not. But the determination of the scope, it tends to be semantic in this case, just because we are unlucky and we have unstable functions. Okay, if the functions are stable, then basically you play this game here and this game here, and it's a lot simpler. Yeah, and that becomes mechanical. If you have evidence that your function f is stable enough, you basically perform some kind of sensitivity analysis, and if you reassure yourself that the f is stable, then you really don't have a problem. But in all other cases, I suspect that you can't get away from anything that is domain specific. Okay.
Can we at least determine or be certain about the functions being stable or not? I guess we could guess it from the data, from the history of the data.
So the question is, how do you determine whether it's stable or not?
Yeah, like if we take it as a black box and just looking at observations, if that is enough to be able to sure
it
we
could,
can apply
yes,
it or not.
It could be basically you could try and learn whether f is stable from a sufficient number of input-output pairs, essentially. Okay, because these are not analytical functions; these are workflows, essentially. These are pipelines. So I think the best you can do is accumulate enough input-output pairs, and then again, what you need is simply a metadatabase that keeps around all the past executions, and you run analysis on them. For example, by computing data-diff on the left side, on the input side, and output diff on the other side, and then convince yourself that that the f is well behaved. Really, I mean, I'm not doing maths here. I'm trying to do architecture. So the core of this is building an architecture that is centered around a metadatabase that contains the history of all executions you have done in the past, to the extent needed to determine the potential impact of a new change that you observed in the input. I'll get to that in a second. Okay.
Perfect.
Thank you. Thanks. Right. Okay. So. Yes, this is the conservative approach that I mentioned. Basically, by using that heuristic, instead of about 500 re-execution, you actually do 70. Whereas, as I said, the battle game ideally will give you 14 if you hit every time. But because you are conservative, you have a higher recall, shall we say, and a lower precision, but you don't generate false negatives. Okay, so that's the kind of chapter 1, just to introduce the idea that we convince ourselves that it would be worth actually building an architecture that is designed to make recomputation efficient in response to changes. When does it apply? When the analysis is expensive, the data changes are frequent, and not all the data changes are significant, because if they're all significant, there's a very little to optimize. I mean, if they all are impactful, then there's no option but to recomp every time, and it's not an interesting game. We also make the assumptions that the processes are observable and reproducible, obviously because you want to reproduce the whole process, but also, as I get to in a second, because you would like to optimize within the structure of a process, because a change at some point in the process may require only partial reevaluation of the rest of the pipeline, but not from the beginning. Okay, so intuitively, there's a notion of partial rerun, which assumes that you want to be reproducible ++. Okay, in a smart way. Observable, because we're going to now add the notion of provenance, which is a way to observe the execution and record the trace of what exactly has been executed. Which branches of the workflows have been touched by which data items in the input or in the dependencies. So so the main idea is to replace re-computation with a step of estimating the impact of a change, and then try to perform partial re-execution where possible. So we try to do two things specifically, and this is our hypothesis. If we collect enough provenance or log enough metadata from the execution, is it true that we can identify the subset of the executions where high impact from change is likely? This is the scope, okay? I'm not going to talk any more of that. I gave you a little hint that we had a very quick discussion on this. And I'll focus on the second part instead, which is identify and re-execute the minimal fragments of workflow, which is the partial rerun part. And again, you may be disappointed that I'm not covering much of the details. This is very high-level overview. There's a fairly intricate paper that I can point you to for more details. But just to give you an idea of where we're going with this, so notion of reproducibility normally focuses how to reproduce. So make sure that if you press run multiple times, possibly with some variations in the inputs or some variations along the structure of the process, nothing breaks and you get results that are valid on the other end. Okay, the ReComp framework is to focus on a complementary notion of why would you reproduce, when, and to what extent. Okay, so that's just to position things. And so that means which subset of individuals, the ones that had the black, we said this, but also now which process fragments, and this is the idea of partial rerun. So for example here, if the change is only in cleanvar, then the scope of the fragment that you want to reproduce is the red one. If it changes in GMAP, which is the other reference data set, is only on the blue one. And this is basically an implementation of the little workflow using actually a workflow management system, which is called eSign Central, developed here in Newcastle. It could really be anything, but it's a data flow, so it's intuitively kind of easy to instrument with provenance. And by using provenance, we can actually now do this automatically. So this is completely mechanical and does not require any domain knowledge. So that's kind of the good news. So the ReComp is effectively a meta process, which means there's an analytic underlying process P, and we look at that process and execution. We have a login element, which is normal, and logs into a history DB. But history DB is not just a log; it's just a system log. It's a provenance store. Okay, I'll get to one slide about provenance here. And then what happens is change events occur. So, okay, new version of cleanvar has just been issued. That triggers my computation, which is event-driven, and it's driven by change events. And as I said, first thing I do, I quantify these changes using a collection of data-diff functions. And these are the plugin points. So this is a framework with a couple of plugin points. One is that you have to be able to differentiate data of different types in a way that sometimes is just not purely mechanical. Okay, I mean, if you have a set, the difference between two sets is obvious, but I don't have the slide here, but you can actually easily see that you're only interested in changes in some of the variables associated with a record, not in others. And if the others change, you can ignore it and so forth. So you have to customize this data-diff. And then the core is to now estimate the impact of changes. And here you have to plug in your impact estimation functions, such as the heuristic that I presented. Okay, and I don't think there's anything magic about that. But what it does is help by the history database, because it pulls all the past diagnoses, in this case, all the past executions, and determines which ones are in scope conservatively again, or not conservatively, depending on your application. And then the bit that I will talk about for a couple of minutes here is the optimization stuff, where you want to carve out the sub-processes. That's a partial rerun. And now, just to complete the ambitious picture, is that now you not only want to be able to re-execute the whole process on the data D, but now you have, so D is the old data that one instance of the process, one patient, okay, was executed on, and so P was executed for that patient, or let's say for that patient with that set of dependencies, with that version of the database. I now have a new version D prime of the database. I decided that patient is in scope. I also have a new version of P, which is called P prime, which is a cutout of P, and my ambition is actually to re-execute P prime over D prime. And that basically is that's what I send to marine time, basically. That's what I submit for execution. And that goes around the loop again. So this history database, if you're still with me, is crucial at the core of everything in here. Okay. So briefly, this is not a game that you can always play. It has to do with how transparent the process is. You can go from a situation where you have a black box process, and the execution trace is just IO provenance. All right. So basically, I can look at the inputs and the output, but nothing in between. There's very little chance here that I can do partial rerun. But there are good examples. We have another case study, which is a simulator, which is a black box. Not much luck there for partial rerun. We can do clever impact estimation on other case studies, which we have illustrated elsewhere, but we can't do partial rerun. Okay, we want to do both. Then we have to be in essentially this situation where you have a white box situation, which now allows me to capture step-by-step provenance, and then use so for example, a workflow. Your R or Python code is open enough to do that. And actually I'll illustrate in the second part of the talk if I get that far. And then now I have a fine-grained impact, and I can play this partial rerun game. So there's a notion that there's kind of technically complicated, I would say, well, not complicated, but it will take a lot longer than the time I have here to explain this how provenance is used in detail in this. But there's a little paper here that you can look up. You can have the slides, by the way, of course. And that's because I also want to leave some time to talk about the provenance for data science bit. So that's what I don't do complete justice to the work. But just as the high-level overview, what is provenance for those of you, probably many who haven't heard about Prov? So Prov is a data model / ontology. Yes, there is also an OWL version of it that became a standard at the W3C in 2013. I was instrumental with lots of other people in shaping this standard. This is a super high-level view where you have entities with derivations. Think entities can be anything, but in this case are data. And so you have data derivations that you track. And the derivations occur because there's some process, workflow run, some programming execution, or some method call if you want inside your Python code. It depends on the granularity. Okay, you can choose that used some input entity, some input data, and producer. So it is a producer-consumer relationship between these two pieces of data. This is mediated by an activity, which is a process and execution at some granularity, and that sometimes implies an actual derivation. And the ambition is to use this. This framework, which is actually a lot more complex than this, to track the provenance of a little workflow as it executes and then use it for partial rerun. Again, I'm skipping lots of details, but the fundamental idea is every invocational workflow generates a provenance trace. So if this is a fragment of the workflow, a workflow contains a couple of blocks with a connection between them. Then in Prov parlance, we called it a plan, and we can have basically a formal representation of the static structure. The program is included in a workflow. Workflow consists of programs, blocks connected by block, blah, blah. And then there is a dynamic or runtime view of these. So when we observe this process in execution, then we have counterparts here. For example, B2 exec is an execution of B2, an instance of B2 in execution. It used a particular input data item. And this data item was used by B2 and it was generated by B1. So it goes in the opposite direction. Okay, so B1 comes before B2. So B1 executes, it generates this data, which is then later used by B2. And that is consistent with the fact that there's a channel between B1 and B2. Okay, the things go in sync very nicely, so that for example, if I now annotate this by saying, well, B1 exec used a database, so this is now your cleanvar, okay, is a particular instance of cleanvar, which I have notated as instances of this particular version. Cleanvar is also an entity which is being used for the purpose of computing B1 and blah, 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 okay? So if you keep this, and you can actually completely reconstruct this provenance automatically in this case from the workflow. We do it with Design Central. You can do it other workflow management systems. It has been a popular thing to do in the Science UK program years ago. Okay, so we do have this. And so now, if you have this workflow, which, as I said earlier, I mean, this is the abstract version up here. This is actually how it is implemented with the three phases: the phenotypes to genes, which is this, the variant selection, which is this, and the variant classification, which is essentially a combination of blocks that internally are black boxes. We don't care what they do there. We don't capture the provenance within the black boxes. But we now are able to use the provenance. Basically, I omit all the queries on the provenance database, but because it's a formal model, in fact, you can do RDF, you can do. We actually use Neo4j to store this provenance, so these are Neo4j queries. And fast forward to the result, we can tell that, well, a change in cleanvar will only require executing this, and changing gmap only require executing this, and which some savings as a result. And this is done completely mechanically, completely independent of the domain, so it is a kind of decent result, I would say. Okay. Right. So the catch here is that obviously at the boundaries here between the boundaries of the red and the blue here, you have to cache intermediate results from the previous process execution. Okay. So if you do this analysis up front, that you know that you need to cache this 133 meg worth of data, because this is where you restart. So basically, you need this because you're not re-executing we are not re-executing the red when we are executing the blue. So the input to this join here will come from a cache instead. Okay, and vice versa. If we only execute the red but not the blue, then these 37 kilobytes must be cached to be used as a join, as an element input to the join. Okay.
So are we here certain that the cache will not change? Like that, using the provenance data or the provenance metadata, we can tell that let's say the red one will not change the output at all, and that's why we can do the caching.
Yeah.
Or
yes, exactly. So yeah. So basically, if you observe a change only in cleanvar, you know that you don't need to execute the things that are only blue. Okay. So basically, you can save these these parts here, because they change only affects, because basically intuitively, clean var only comes in here, and so it's pointless to rerun everything here. Okay, and you can use basically the structure of the workflow. We prefer to use the provenance. We think it's a more general approach to determining exactly which bits are affected by a change. Yeah. Okay. Right. So let me summarize on this part. Basically, it's a genetic framework where the genetic bit is a provenance database with its collection capture capability, and then because it's a framework, you can customize it, but you know exactly where to customize it, and we have separate studies of what it takes to customize this. If you want, for functions that are domain specific. If you want more details, this is one kind of final reference for 2019. Okay, let me move quickly to the second part, and probably have a little more than 10 minutes. Maybe I claim the fact that we got a couple of questions, but we'll see. Again, this is a second type of usage for data provenance, which I think is useful to better understand your data science pipelines, specifically when the pipelines are complex, like in this case here. So, and we kind of ignore all the machine learning machinery that happens here. Lots of model explainability has been done in the machine learning community. Relatively little has been done to try and understand what happens during this preparation for learning phase, where, on the other hand, we should be aware there's lots of the decisions that are made here are critical to the effectiveness of the model, not just for performance, but also correctness. Are we, for example, rebalancing the classes in a way that avoids overfitting, or are you introducing bias in the data in the training set? And in general, so the game is that I want to go backwards again from a model, okay, from a model, and this is a provenance graph that tracks back from the model all the way, say, the training set, all the way to each of the steps that were followed to get to the training set. So that when I see a particular, and in a very granular way, if I see a particular value in a cell of my data frame that I use in my training set, sorry, this has value 32, I can ask, why is that 32? Has it always been 32? Has been the output of some imputation step? Has been a regularization step? Or sorry, normalization step? Why is this feature here in the training set appear that is not in the original? When was it introduced? What was used to engineer that new feature? All these questions that I believe a data scientist / data engineer should be able to ask. So, and then again, there are limitations to what we can do, right? If we have a process, it's like this is one step in a pipeline, which is completely opaque. There's very little that we can say. We must assume that all outputs depend on all inputs because you have no further information. Not very informative, not very useful. You can get to a place where you have transparent programs. For example, if this is the logic, well, they can infer from the logic that Y1 only depends on X1, but not X2, whereas Y2, trust me, believes depends on both of them. Okay, and if you can do that, then the next ambition step in terms of ambition is to open up the data and say, okay, well, now I have fine-grained data sets. So this is the data; these are all data frames, and I may be able to say that a particular element in the input depends on a particular element in the output depends on element in the input, one or more. And actually for I'm sorry, these two are Y2, yes, that's fine, Y second, okay. And so forth. So this is more granular. And finally, if we have all these programs, these steps that are that allow for granular inspection, then we have the most granular provenance that we can achieve. And so our investigation is basically what happens in this extreme case. How much provenance do we collect, and how do we do that efficiently? And so to do that, and semi-automatically, okay, which means that we need to start from understanding what the operators are that can make up a pipeline. And so the idea is that out of many operators, this is like the scikit-learn view. This is the another workflow management view of those. They're pretty much all the same, but they all fall into three big categories. And it turns out that for the purpose of provenance, the capturing the patterns for each of these categories is enough. Okay, so that's good news because we don't have to exhaustively chase all possible operators. And I'll give an example of vertical augmentation, which really means engineering a new feature in your training set. So basically, you have an operator that changes either the value or the shape of a data frame, and this is kind of the main distinction that we make. So vertical augmentation adds a column or one or more columns. For example, here I have a table where I have age, and then I engineer a new feature that binarizes, binarizes age as a young or adult depending on an age threshold, and that's the function. Okay, and so the game here is to associate a provenance, a little provenance fragment to this transformation here. Again, this is an activity, entity, but now the entities are the individual elements within this framework because we can observe all of them. We did this for basically Python and Pandas, essentially. And you come up with a little provenance fragment that looks like this, right? This is the instance of the activity, which in one case used the input 24, which is this, and produces young, which is this. And then in another case, I used 28 and produced adult, and I omitted the others. Okay, so basically there's one little fragment of this provenance for each of the cells in the data frame, so that I can ask, why is this young? Oh yeah, I look at the provenance because the age range function decided with this particular, annotated with this particular threshold, decided that it was young because the input was 24. Okay, so you come to explaining why some data is there. And the clever thing here, the interesting thing is that the provenance structure is very regular in this case. It's basically a repetition of the same pattern over and over again with different instantiations. And therefore, we use a template and a binding approach. So we design these templates once and for all, and we have one for each of the three categories, plus joins and appends that I'm not discussing. And basically, a provenance pattern is just another little provenance fragment. I call it provlet, which contains variables. Okay, this is actually valid prov. Prov is a notion of namespaces, so I can actually write this in prov. Fine, interpreter will not break. And then when I observe the operator in action, all I have to do is basically build up a little database or a table of bindings that says, well, these were the old values, these are the new values, where these are the variables, that are mentioned in the pattern. And then I can bind these values to the pattern, and I basically have this cookie cutter approach where I now generate a new instance of this pattern for each of the elements in the cell. So again, I don't want to overrun here. So very quickly, I can do this for all the operators, as I said. What is interesting is that I can at least semi-automatically do this by not having to do code inspection statically, but all I'm doing is basically observing the program in action. So it is an observer pattern. An observer is a tracker. So now you have a data frame df, and what I do is I create a provenance tracker that encapsulates df in my data frame. Okay, and every time data frame changes, the provenance tracker is aware of it, observes it, and does its provenance thing. And it does basically it does this bit here. Okay, so that's quite elegant. And it seems to work fairly generically. So for example, here is, okay, so there's no more, there's too much detail, but for example, this code here essentially generates, does a one-hot encoding out of one column of categorical variables, actually of a number of columns, in fact. All of these are categorical, and it does one-hot encoding of each of them. And we are, in fact, able to, because we have this tracker here, to track the fact that columns are added, and in the end, each of these columns here are removed because these are the original columns. But columns are added as part of this one-hot encoding. So the observer does not know about one-hot encoding, but it detects a shape change as well as a value change in the data frame. That's all it does, and it seems to actually work quite effectively in this case. Right. Maybe a couple of minutes on evaluation. We have two types of evaluation here. How do you decide what provenance trackers to use? No, is no input from the subject expert. Well, basically, you can track any data frame you want. So any data frame whose changes you want to track, you encapsulate into a tracker. The more you do, the more you pay in terms of overhead, and I'll get to that in a second, because there's a price to pay to observe to an observer pattern at runtime, as we know, but it's otherwise entirely your choice as an analyst, essentially. Yeah. So you minimally instrument your code to play this game, but it's your decision which data frame you track. In the case of joins, you actually track two. There's an extension to this, but that's just a detail. Okay. I hope I have answered. So there's two types of evaluation. One is, there's a number of standard data sets that are used in the literature. We basically took three of these: German Credit, Compass, and Census. So this is an example of Census, which is actually the heaviest one, essentially because it does one-hot encoding of seven categorical variables that we have seen, and that is a heavy operation to track. Lots and lots of new data added. It's also, and there's evidence here, okay? So basically, the Census original record as data set has 32,000 records. By the time we're done with this apparently deceptively simple set of transformations, you end up with something like, what is that? Nearly 4 million provenance entities, because basically we're keeping everything, right? And some kind of 10 million provenance relations that we can use to traverse back. Yeah. Incidentally, this is already optimized, meaning that if nothing changes to a cell, it's not like we blindly copy over the entire data frame. We only create entities for things that change. But because one-hot encoding here is kind of heavy, it changes a lot. That's where the complexity comes in. And so this ratio may change depending on the nature of the pipeline and the nature of the operator. Okay. So the clerical clean on every cell removing blanks, if it removes a lot of blanks, I keep track of that. Okay. So I don't have the possibility to, maybe I could potentially turn off tracking for one particular operator if I think it's not interesting, but then it gets complicated. Okay. I see another question. Let me please move forward here. It seems no, maybe it is relevant now that I read it. Yes, it is about trusted AI. While data provenance is highly relevant, there may be some changes that we may want to ignore. Mechanisms available to filter out the changes in data that may be triggered by bad actors. Yeah, so as I just said, so there's two ways, okay, that come to my mind. One is you decide to ignore some of the operators, okay, if you know that you don't want them, but it's hard. Yes, I mean, So I think what you're trying to say is that can I actually use this to skip changes that I discover that are not that were not appropriate? And that's actually a very interesting idea. If I interpret your question, right, which I hadn't thought about. So yes, potentially you could, but you end up in a place where if you omit one step, you have to kind of backtrack all the way. So you can't just pretend that it didn't exist and move forward, because what follows is a consequence of that step. So you can't just skip it and ignore it, right? You have to, once you detect, it's a kind of partial rerun. You get back to that point. That is a kind of a snapshot of where you are, and then move forward again without that step. I think that's probably the best you can do in this situation. Yeah. Yes, I think we could argue that that is an innocent until proven guilty approach. But technically, the fact is that if I inject a step that you don't agree with, and the pre-processing gets to completion, then the moment you disagree with that step, I can't use that. You can't use that result. You have to roll back up to the step prior to the ones that you don't want, and then roll forward again without it.
Maybe what it could help with is actually at least understanding the difference, like what has changed between the two rounds, so that it can be identified, like what was the change in transformation.
Absolutely, yes, no, absolutely. And so that you're touching upon another important use of this, which we have not yet explored, which is we call provenance diff. We did some work on provenance diff, so the difference in two provenance graphs based on the evidence that two outputs are different. And there the question is, when do they begin to differ? So basically have two provenance graphs for each of the two executions. And you traverse them backwards by trying to pairwise match. So it's a graph matching problem here, until you come to a point where either where you basically discover what has changed and what is the root cause of the changes in the outputs that you observe. Absolutely, yeah. If you understand the intuition is that's yeah. I can point you to another paper that we have from several years ago, but provenance diff is exactly one of the things that is on our whiteboard. So thank you. Yeah. Okay, so let's wrap up quickly. So as I said, there's one type of evaluation which uses these as benchmark data sets and have an idea of basically. So in provenance, the main cost is the overhead in observing the process and basically recording at the same time. And you can record asynchronously. You can play all sorts of tricks that you're very, very familiar with to record back while the process is executing. But pretty much these are the times. As you can see, basically the two charts on the right one is on the census, which is on a different scale because of its complexity. So we're not really hiding the fact that there is overhead. But in other cases here, the overhead is kind of very compatible with the so basically it adds a couple of seconds, okay, adds a second and a half to the execution. So it is overhead, but it's tolerable. In some cases, these are worst case scenarios that we need to look out for. And then you have a scalability analysis, and maybe just as well go through this very quickly. The idea is that now, as you know very well, that you have types of tests, what kind of operators you're testing on three scale factors for synthetic data sets. And we generate the data sets synthetically using the TCP-DI, which is data integration TPC benchmark. It has a data generator there. And so we can actually control how big these are. Okay, and these are the few numbers, just to basically say that we've done kind of our I'm sorry, I find the chat a bit distracting. let me roll back. Okay, so with this database size, then we have the corresponding storage cost for each operation here. Okay, independent of any pipeline. It's just naked operators one at a time. And this is the time, the space that it takes to store the provenance in Neo4j in this case for each of the operators for each of the scales. So you get an idea. Right, this basically says that we scale kind of okay. I think we scale in a fairly predictable way, so things are under control. What I think I don't have, incredibly here, is the reference to the main paper that we published on this. So I'm going to put it on the slides. I'll put it in the chat maybe. It's a VLDB paper that appeared last year, and we now have a follow-up with these results that presented are actually a second implementation, and we just submitted a journal version of the paper, so fingers crossed. Fundamentally, what I've been talking about here for way too long is the two kind of uses for provenance in two completely different contexts. It's basically process provenance, coarse granularity at workflow level, and kind of data provenance across the process at the finest possible granularity that we can afford, given the transparency that we're given by the program and the observability given by the runtime. So one question is, what's the killer app for such granular provenance? And you hinted at, difference in provenance is, for example, one of these, identifying the impact that a bad operators had on the result, and so forth. That I think that is actually an excellent way to close. So thank you very much for listening. I understand we do have time for question. I'll dig up the missing reference and put it in the chat. And I have no idea why it's not here. Right. Thank you very much.
Cool. Thank Paolo for a wonderful presentation and very interesting topic. I don't see any questions right now on the chat, or those that we have not addressed yet. I have one question about you talked about the provenance on the workflow level and then provenance on the single process.
Yeah.
How about combining those together? And the reason why I'm asking is that you have the output on the whole workflow, understanding for each column or even each value, like what sources were used. I think we would need to combine both the workflow level and the process level to be able to answer those questions.
Yes. So in these, can you still see? I don't know. My other window is frozen. Can you see this scrolling?
We can still see the slides and changing.
Oh, okay, because it's frozen on my stuff. Okay. Yeah. So for example, this here's what we know about the process. Okay. We actually have the entire structure of the process indirectly through all these derivations. It's through the data. So there's no workflow here that says A followed by B followed by C, but rather is A generated X, which was used by B, which produced Y, which was used by blah, blah, and so forth. So it's indirect representation of the process structure as observed at runtime, as opposed to being pre-specified at so there's no workflow, in fact. So we don't do program analysis here. But yes, I think this does provide a combination of both. In the previous case, like in ReComp, you would have kind of the opposite. So you have a clear notion of the static structure, but you may be unable to dig into the details of each data item because maybe it is a black box. It is okay, but you're right. I mean, so there's actually a piece of work done quite a few years ago. I think it's called putting lipstick on a pig, or some very curious paper title. which basically says, well, to the extent that each of the blocks in my workflow are database queries, then I can be very granular about the data, the input and output to this block, and I have the benefit of both. But this kind of seems a bit of a special case. It's written by people who only see databases in their lives and say, well, everything you do is a query to a database. But in this case,
seems a bit
absolutely
strange.
Yeah.
One more question, and perhaps the last one from me would be, and we have one more. So if you want to read it yourself.
From Heidi. Hi, Roy, by the way. Nice to see you. So I wonder whether it's useful or the approach might also be useful in a project where we have for running, tuning, test, and operating system where we change selected items. Yes, it's basically them kind of sweeping, parameter sweeping. And the testing tools and OS evolves in a way that's similar to how the genetic testing tools evolve. Yes, that's kind of the idea. Yes, you have. That would be very interesting to try out. In fact, so. Yeah, to the extent that you can actually describe what the testing does, so if a testing is an interesting enough process, it's not a complete black box, it's not a complete black box, then yes, I think that there'd be something to do in terms of understanding what has caused a change. I just realized I'm looking at the wrong camera. What is called a change? So short answer, I think it's yes. We can talk offline about this. I'll be very happy to. Yeah.
I was one more question, which is like, is there anything on GitHub or some open source project that could be used to look at how the thing is done or play with or applying in people's use cases and see how it works?
So I was afraid you'd ask this question. So we have a demo and we never got to the point where it says here's a download link for ReComp. So I have to get back to you for that, because the person who is responsible for the demo is still around and is actually here, but it's not a kind of download and try kind of thing. We can try and arrange a demo for you by talking a little longer, probably. Yeah.
Perfect. And the same also, it was very interesting to see how the provenance of the pandas transformations is done. And again, like I guess more people here would be interested in how that works.
Yeah. So let me dig up. Oh, this is complete. This is very. I got very strange effects. Let me unshare this. Hopefully, yes, and then regain control of my machine. Not too late. I'll do that later. And even I'll send you the link. I lost control of my laptop. The other one, so the second part is easier. We actually do have a Git repository with the code, which you can try yourself. It is obviously very much prototype stage, but yes, that is easier to achieve. If you have an interest in that.
Perfect. I think many people here enjoy prototypes, so don't be afraid about that.
Yeah. Okay.
Cool. I don't think we have any more questions here, so we might be wrapping up. I don't know if Matthew will show up to call this presentation finished. Here we
Well, I'm back. So big thanks,
Hi, Matthew.
speaker, to our conversation lead, and everybody who showed up. This was a very interesting discussion, even from my end. And hopefully we'll be able to share contact information for everybody. So if you'd like to get in touch with Professor Messier, we'll be happy to provide contact. And also, if you have any ideas for future topic for Research Day, we are listening. Thanks everybody for showing up, and See you next month.
Thank you very much for having me. It was a pleasure. I hope it was interesting, and I'll send even a link to the VLDB paper, which I'm very proud of, and it's not referenced incredibly. Take care. Thank you very much.
Thank you very much.
Bye.
See you.
Bye everybody. Bye bye.